In this video, I'm going to be upgrading the system memory on this Lenovo Legion Go handheld computer. Now, for those of you who may not know what the Legion Go is, basically it's a small handheld high-performance computer mainly designed for gaming. Now, it is very similar to the Steam Deck. However, it is not similar to the Steam Deck in one significant way, and that is that it doesn't have built-in controllers on the device itself like the Steam Deck does. Instead, it uses more of a Nintendo Switch style method of attaching controllers using these little rails on the side here. Now, as I mentioned in this video, we are going to be performing a system memory upgrade on this Lenovo Legion Go, and so let's go ahead and take a look at the initial system specs here. So you can see that this machine currently has 16 gigabytes of system memory installed. You can see right there. It has a Ryzen Z1 Extreme CPU running at 3.3 gigahertz, so definitely significantly more powerful in that regard than the Steam Deck is. But like the Steam Deck, this machine only ever came in a configuration of 16 gigabytes of system memory. Now in this video, as I mentioned, I'm going to be upgrading the system memory, and I'm going to do that with these chips right here. Now, I purchased these chips from China, of course, and these two chips right here will give me a total of 32 gigabytes of system memory in the system. Now, if we go ahead and take a look at the bottom of them here, you can see the ball out and pitch of that BGA footprint there, and you can see it is quite different from the RAM that the Steam Deck uses. In fact, I've got a chip of that right here, so you can see this module right here has a much lower pitch or higher pitch. I don't really know. I guess what you'd say, much bigger pitch, I guess is the correct term. And then this chip that the Lenovo Legion Go uses has a much smaller pitch, and also, of course, has much smaller solder balls as well. So with that, we're going to now begin the process of upgrading the system memory in this system. So, of course, the first thing we need to do is get the machine taken apart, get the motherboard removed, and then from there we can begin the process of removing the original chips. Alright, so as you can see here, I've gotten the board removed from the system, so we can go ahead and take a close look at it here. And you can kind of see the original part number on those RAM chips there. And of course those are the chips we are going to be replacing in this video. So if we go ahead and compare them with the new chips that we got, you can see that the size of them is exactly the same there. And so that means we do have the correct chips. Of course, we'll check the BGA footprint once we get the chips off of the board. But with that, that is the next thing we need to do. So I'm going to get this board up on my board preheater, positioned right underneath these RAM chips here, and then we will begin the process of removing them using my hot air. Alright, so as you can see here, I've gotten the board up in my preheater here. So the first thing we need to do before we start desoldering the chips is we need to remove these little pieces of edge bonding on each corner of the chip. Actually, there's only one on two corners of each chip, so it helps a little bit there. But now that the board has been heated enough with my board preheater, we can go ahead and just remove those using a pair of tweezers. Alright, and now that all the edge bonding has been removed, we just need to turn on the hot air. I'm going to heat the chips to around 330 degrees Celsius, and then we're just going to go ahead and remove them. Alright, so while that's warming up here, let's go ahead and first apply some flux to the perimeter of each chip. Alright, and with the flux applied, we're just going to take the hot air and start removing the chips. Alright, so as you can see there, the chips have both been removed. So now we just need to wait for my hot air to cool down, and then we can begin the process of wicking the pads and removing all of the residual solder. Alright, so now that I've gotten the chips off, we need to just remove all the residual solder using my soldering iron, some leaded solder, and then some solder wick. So we'll start by just applying some fresh leaded solder to the pads, and then from there we'll wick the pads and make sure all the solder is removed. Alright, so that's all the solder successfully removed, so now we just need to clean off all the residual flux with some rubbing alcohol and a paper towel. Alright, and that looks really good there. So the next thing we need to do is apply some fresh flux to the new chips and prepare them to solder them onto the board. Alright, so as you can see here, I've gotten the two new chips up on the preheater here, so I'm just going to apply a little bit of flux to the pads here. You don't want to apply too much, or otherwise it'll kind of run underneath the chip and make it lift up when you're trying to solder it down. So we'll just apply a little bit here. And now that that's applied, we'll just take the chip, hold it over the hot air or the board preheater, and let the flux melt onto the pads. And we'll take some paper towel and wipe away some of the excess here. Just like that. And then we'll do the same thing with the other chip. And there we go, the two chips are now ready to be soldered onto the board. So I'll get the board back up here and we'll prepare to solder them onto it. Alright, so we've got the board warming back up on the preheater. So now we're just going to take a little bit of flux and apply it to the pads. Wipe away a little bit of the excess. And then we will align and heat the chips to solder them on. Now you can look at the board, the silkscreen outline does tell you where pin 1 goes. So on this chip, pin 1 goes towards this corner here. And the other one has pin 1 at this corner up here. So we'll align them accordingly. Now, once they're in place, you want to take something and just verify them and make sure they're fully aligned exactly into position. As I showed, these are pretty tight pitch solder pads or solder balls, so you want to make sure they're pretty well aligned there, and that looks just about perfect. So now I'll take my hot air once again at 330 degrees Celsius and solder them onto the board. Alright, and that looks really good there. The chips look to be fully soldered. So I'll go ahead and give you a closer look at them real quick, and then we'll reinstall the board into the chassis, give it a test, and make sure the machine still posts. Alright, so as you can see there, the chips look to be really well soldered. Let's go ahead and get a different look at that. There you go, you can read the part number right there. And if you take a look, the silkscreen outline, they are perfectly aligned in the center of each outline for each footprint of the chips there. So everything looks good, and if you look at them from the side, you can see that they are fully flat to the board. They're not raised on any edges, and everything there looks good as well. So it all looks to be soldered on successfully. So now, like I mentioned, I'm going to reinstall this into the chassis, get the heatsink and everything installed. That way we can give it a initial test just to make sure the machine still posts with these new chips installed. But at this point, the machine will not detect all 32 gigs of installed memory, as we still need to edit the SPD data in the system BIOS for it to detect the entirety of each chip that we installed. So with that, I'm going to get the board reinstalled into its chassis, and then we'll test it and ensure everything works as intended. Alright, as you can see here, I've gotten the Lenovo Legion Go somewhat reassembled here. I did leave it mostly apart, of course, because I'm going to have to take it apart again to modify the SPD data. But let's go ahead and power it on and make sure it works. And there we go, that's a good sign. And we've booted into Windows successfully. So just for the heck of it, let's go into settings. It's still going to show 16 gigs, like I said. Yeah, so there it is, 16 gigabytes of system memory still detected. So yeah, that means that at least the chips are working, the chips are good. So that's all I really wanted to make sure of, and that of course they were soldered on successfully. So now with all that confirmed working, now we need to take the system back apart and desolder the SPI ROM in order to dump it and modify the machine's SPD data in its BIOS. Now, if you saw my previous video about doing this modification on the Steam Deck, you would know that I just flashed a pre-modified BIOS image that someone had made with that SPD data already modified, and I could just flash it with the standard Windows or Linux H2O BIOS updating utility, and it would just flash it on no problem. However, in the case of the Legion Go, there isn't any such modified BIOS image that I can find anywhere, so we will have to do the modifications manually. But because we have to do that, I can show you exactly what needs to be changed in the SPD data in order to make this work. So that way maybe you can understand what's going on here a little bit better in the case of the Steam Deck when I just flashed a pre-modified image on. So with that, let me get the board back out. We'll get it on the preheater once again and desolder the system's SPI ROM. Alright, so as you can see here, I've got the board back on the preheater once again, and the SPI ROM on this board is located right here. So of course that's where our BIOS is going to be stored. So of course, like anything else, the first step is to apply some flux to it. And then we will simply heat it with hot air to remove it from the board. Alright, so as you can see there, the SPI ROM has been removed. So now I need to get this attached to my EEPROM programmer, and then from there we can begin the process of dumping and modifying the ROM. Alright, so as you can see here, I've gotten my EEPROM programmer out and ready, and the chip in question is located right here, as you can see. So you can see it's a standard SOIC8 style EEPROM there. And in order to use it, I've got a little adapter here that I'm going to put it into. So let me put it in here. So the adapter looks like this. You can see I've put the chip in that side of it there. And then just close down the flap like so. And then we can put it into the programmer. Now, before you try to read from this, you want to make sure that your programmer actually supports the voltage of this chip. Now, this is a 1.8 volt EEPROM, so you must ensure that your EEPROM programmer supports a 1.8 volt level and VCC voltage in order to read and write these EEPROMs. Now, if your programmer doesn't, you can use what's called a level shifter, which I actually have, and I thought I needed it for this one, but this programmer actually supports a 1.8 volt mode, so you do not need to use a level shifter for 1.8 volt EEPROMs with this particular programmer, which is the XGACO TL866 Pro. So with that, I'm going to switch over to the computer here, where I will show you exactly what needs to be done to dump, modify, and write the modified dump back onto this EEPROM. So with that, let's begin that process. Alright, so as you can see here, I've gotten my EEPROM programmer software open now, and I've already actually gone ahead and selected the correct chip that we need here. But if you need to do that, you just click up here, at least in this particular piece of software. I mean, it'll vary depending on what EEPROM programmer and software you're using. But in this case, it is a Winbond W25Q256JW EEPROM. Actually, it's technically W25R256, but it's the same thing as the W25Q256. So we'll go ahead and select that. Like I mentioned, this is a 1.8 volt EEPROM. So once your EEPROM is selected, you want to just select ID check and make sure your EEPROM ID is detected, so that's good there. And once that's done, let's just read the current EEPROM. So this is a big EEPROM. I believe this one is 32 megs, or 256 megabit, so 32 megabytes. So yeah, we'll just wait here until the EEPROM has finished dumping. Alright, so as you can see here, the dump has completed successfully, so now we just need to save it to a file, and then from there we can begin editing. So we'll go ahead and save it here as Legion Go original.bin. And the ROM has been saved successfully, as you can see. So now we need to open up that ROM in a hex editor. So there we go, there's our ROM, and there's its contents right there. So once you've gotten the ROM open, the first thing you're going to want to do is locate what's called the APCB file inside the ROM. Now normally I would use UEFI tool for something like this, but for some reason, at least in the version of UEFI tool that I use, I couldn't get it to properly find that location as like a discrete file. So I don't know if UEFI tool works properly with AMD BIOSes, or if there's just something I'm not looking at correctly, but we're just going to do it manually in a hex editor. It's really no big deal. So you want to go up here, select find, and then text string, you're just going to want to type in APCB, just like that. And that's not it there, so let's find again. That's not it there. And there it is right here. So you can see there is SPD data in this section for various different memory configurations, which is kind of weird because the Legion Go, like I mentioned, only ever came with 16 gigs of memory installed. So the fact that there's like 5 or 6, if not even more, memory config SPD data entries, that I find that kind of strange. Well, anyway, from here, you're going to want to select this entire section. So keep your cursor up at the top here and scroll down to the bottom. It's not very long. And there's the bottom of it right there. Just shift, select. So now that section is selected. You can see the highlighted length here, 1C30. Select copy. And we're going to say file new. And then in this new file, you're just going to paste in the content that you copied and make sure it's in there. So that way you've extracted the APCB file independently of the ROM itself. So we're going to want to go ahead and save that. Say Legion Go APCB.bin. Just like that. And the next thing we need to do is we need to open that file in a hex editor. Actually, it's already open right here because I literally just saved it. And now we need to modify the SPD data appropriately. So in order to do that, I've actually got a copy of the SPD spec right here. So we'll go ahead and open that real quick. And this, of course, is from JDEC. Now, this is for LPDDR3 and LPDDR4, but it seems to correspond correctly to LPDDR5 as well. And we are actually going to be making 2 modifications to this SPD data. The first modification is going to be done to byte 6. Right here, and you can see byte 6 corresponds to the SDRAM package type. Now, before we get to modifying, we want to find a piece of SPD data to modify, and in order to do that, you're going to want to look for a specific set of hex values here that represents the beginning of a piece of SPD data, and that is located right, let's see if I can find it, yeah, right here is that string. Right here, 0200480000000000. So just copy that, and then if you go search find to hex values here and paste that in, you'll find each piece of SPD data. So if we find again the next piece of SPD data, find again the next piece of SPD data, and so on and so forth. But we want to find the piece of SPD data for the chips that we currently have installed, which are these chips right here, if you remember from earlier. So we can find the beginning of that SPD data, which is going to be, you can just click up here and find again. There's the beginning of the data. Now this piece of data is just a header, but the actual SPD data starts here. So according to that SPD specification document, byte 0 is this 23 here, byte 1, 2, 3, and so on. So we want to go to byte 6. 0, 1, 2, 3, 4, 5, 6. And you can see that byte is 9.5. So if we go ahead and open up a calculator here, we go into programmer mode, go to hex, and we go ahead and type in 9.5. You can see the binary representation of that right here. So if we go ahead and go back to here and take a look at what this means, you can see which each bit corresponds to based on this data here. So we can start at the beginning, 0, 1, represents byte 16 signal loading matrix 1. We're not going to mess with that. Bits 2 and 3, these two here, 0, 1, 2 channels. These bits here, 6, 5, and 4, 0, 0, 1, 2 die. And then bit 7, 1 non-monolithic device. We're not going to mess with that. But what we do need to mess with is dies per SDRAM package. And that is currently set to 2 dies, and we need to change that to 4 dies. So all we need to do is change bit 5 to 1. So we find bit 5, which is right here, and change that to 1. So now you can see that hex value is B5. So go ahead and just modify this to B5. And now that piece of data has been overwritten. Thanks, Windows. So that piece of SPD data has been overwritten. So now the next one we need to mess with is bit 12, or byte 12. So that's byte 6, 7, 8, 9, 10, 11, 12. So 0, 2 right here. So let's go ahead and take a look at what byte 12 corresponds to. And that corresponds to module organization. And I'm not going to explain everything here, but basically what we need to change is we need to change it from 1 package rank to 2 package ranks, which just means each chip, instead of having 1 packet or 1 rank per package, it now has 2 ranks per package. So basically 2, I guess, since these are 128 gigabit chips, it has 2 64-bit ranks that are each 64 gigabits in size. So you combine those two and you get 128 gigabits per chip. So we're going to go ahead and modify that. So you can see our original value here is 2. So we'll put 2 in. And like I mentioned, we need to change package ranks per channel from 1 package rank, so zeros, bit 5, 4, and 3, to 2 package ranks. So bit 3 needs to become 1. 0, 1, 2, 3, so bit 3. And that makes that value into A. So let's go back into our data here, make this 0A, and that is the completed modification right there. Now, we've only modified one piece of SPD data in this dump here, but we need to modify all of them. So we're going to copy this initial part of the SPD data here, and we're going to copy this. Now, with that copied, we want to locate and replace every piece of SPD data with this modified SPD data. So like I said, we've copied that. We're going to go up to the top of the file, search, find that beginning string, or that beginning header for each piece of SPD data, and locate the start of the SPD data, which of course is right after that, and just paste right. And we're just going to overwrite each piece of data with the data we've modified. Find again, replace this one, find again, replace this one, find again, replace that one. Like I said, there's an odd amount of SPD data in this dump. So that's the one we already modified, so we don't have to mess with that. Alright, and that is every piece of SPD data overwritten with our modified copy. So the reason I've done this, and by done this I mean replace every single instance of SPD data, is just because there could be different memory configurations on these boards that are set via strap configuration resistors, and we want to make sure, regardless of what that strap configuration setting is on the board, that our modified SPD data is loaded, because we know what chips we installed and we don't need to worry about any other memory configurations. So with that done, we're going to save that file, and now what we need to do is modify the checksum of the APCB file to match, or we need to recalculate the checksum for all the edits we've made to this file. So in order to do that, you're going to use this file right here, this Python script called manedit apcb checksumfix.py, and I will put a link to this in the video description, of course, but this is an implementation that someone has made actually to do this same operation with the a ROG Ally mobile PC, but it works just fine with any AMD system BIOS APCB file like this. And it was actually derived from a file created by some of the Coreboot developers. It's actually located in the Coreboot repositories. So in order to use this, we're going to open up a command prompt. And we're going to cd into this directory here. And what we need to run is we need to run Python and Python 3 if you have Python 2 installed, because this is a Python 3 script. That Python script space the input file, and our input file is going to be our APCB. Let's see if we can just drag that in here. Yep, so there's the path to that. That's going to be our input file. And I want our output file to be in the same path, but I'm going to rename it fixed.bin for fixed checksum, and then we're just going to run that script. And as you can see, fixing APCB checksum, everything is now done there. So we've got our fixed checksum file there. We're going to open that up in the hex editor. And you can see the checksum bit right there. You can see it's changed from the original. So all we need to do is copy all of the data from that APCB file, and then go back over to the ROM, find the APCB file again, and there it is, and then we're just going to paste over it with our modified data. So there we go. And yep, we've got that fixed checksum bit of 36 right there, just to verify that. Yes, so that's good. So now we can just save that dump, and of course I'll save as so we don't modify the original. And we'll name that Legion Go modded. Now with that saved, we're just going to open that dump, or that modified dump, in our EEPROM programming software, and then simply write it back to the EEPROM. So of course this will take quite some time to complete, so I'll just go ahead and stop the video here and resume it once the dump has been written onto the EEPROM successfully, and we'll begin soldering it back onto the board. Alright, so the dump has been written back to the SPI ROM successfully, so now it's literally as simple as just soldering the EEPROM back onto the board. So first I'm just going to apply a little bit of extra flux, and now we'll take the EEPROM and align it with pin 1 in this corner as marked on the board. And then we just need to heat it until the solder has melted it to the board. Alright, so as you can see there, the EEPROM has been resoldered on successfully. So now we just need to reinstall the board back into the chassis one more time and test it. And in theory, we should now have 32 gigabytes of RAM installed and detected. Alright, so as you can see here, we've gotten the Legion Go partially reassembled once again. So let's go ahead and power it on again. And hopefully it'll post here. If it does, that means our SPD data modifications were correct and successful. And yes, there it is. It has posted. So that's a good sign. And as you can see here, we're booted into Windows. So let's go ahead and take a look at the system specs. And there it is. Look at that. 32 gigs of RAM installed and detected. You can see right there, we've got 32 gigs installed, 28.7 gigabytes usable due to the video memory using some of it. But overall, I'm very satisfied with the results. That's a successful upgrade. So with that, that has been the successful upgrade of this Lenovo Legion Go from its stock 16 gigabytes to 32 gigabytes of system memory. So with that, I hope you enjoyed this video.